My name is Danny Wallace, and I'm here to talk to you about WebSocket. So first, I would like to start off by thanking Jeeny, Bractlet, and Codesmith for sponsoring this tech talk. Now let's get right into it. So there are four little letters that anybody who has ever used the internet is guaranteed to have seen, right? These letters are so ubiquitous that we usually take them for granted. In fact, your browser is most likely hiding them from you right now in the address bar, just because they're such a given. I'm talking, of course, about HTTP. So when we think about using the internet, specifically as users interacting with browsers, interacting with servers, there are a lot of standards, protocols, and practices, and they're there to ensure that your experience is consistent. Whether you're browsing the web from a laptop or phone, outside or at home, Safari or Chrome, or Internet Explorer, which doesn't rhyme with anything I just said. And now that I think about it, is not a very good example of complying with modern web standards. But nevertheless, HTTP or Hypertext Transfer Protocol is one of those standards. But what if I told you it's not the only one? And in fact, there are other letter combinations that can and often do go before that well-known : // So one of those is WS, or WebSocket. HTTP allows you to reach out to the server, but WebSocket allows the server to reach out to you. So let's dive into how all of this works. One of the best ways to explore what WebSocket can do is by comparing it to HTTP. Like HTTP, WebSocket is a protocol for communication between a client and a server. However, the distinctions between them make it clear that they serve different purposes. So the first main contrast is that HTTP, specifically HTTP1, is unidirectional, right? But WebSocket is bidirectional. So with HTTP, all requests are sent from the client. So say we have a client, Alice, and she's using a browser-based messaging application. Posting a message is straightforward. Alice makes a post request to the server, including her message content and the body of this request. From her point of view, this interaction is complete. HTTP was more than enough for her need to send a message. But what about receiving a message? So here's a different scenario. Say that Alice has a roommate, Bob, who is also a user of this messaging app, right? So Bob calls out from the other side of the room, "Hey, Alice, I've just sent you a message." To which Alice responds, "Why? I can hear, just say your message." Bob replies, "Bruh, it's a GIF. What do you want me to do? Read the metadata out loud." And Alice, realizing this is going nowhere, opens her browser and decides to look at Bob's message. But much to her surprise, there's nothing there. So what's going on here? Is Bob gaslighting Alice? In general, probably, but in this specific case, no. The issue is that this fictitious messaging application that they're using, it's not good. It's sort of like a whack Slack, right? A dull Discord, less like WhatsApp and more like Worst app, you know? It's built entirely on HTTP instead of WebSocket. So when Bob sent his message, that part was fine. He made the request, it went through, but then literally nothing happened. The server can't make a post request to Alice sending her that message since HTTP1 is a unidirectional protocol. Now, there are ways around this using purely HTTP. You could use a process called polling, in which the client continually makes requests to a server in a loop, right? So the browser simply polls Worst app server, basically asking every second or so whether or not there's been any new messages. Get requests for new messages, no new messages. Get requests for new messages, no new messages. Get requests for, bro. They're not going to be, nobody is trying to message you. Your DMs are drier than a well-written code base, okay? So as you can see, polling is viable, but as you can imagine, all these requests become resource intensive, especially when the result of said requests is usually going to be the same thing, an unchanged response. So a refinement of this process called long polling cuts down the resources used by reducing the number of requests made, but it still introduces latency issues of its own. Another non-WebSocket option is server sent events, or SSEs. An SSE actually can use an HTTP connection to send information to a client, but here's the catch. A server sent event is still unidirectional, right? So it goes from the server to the client, but it's not a means for the client to send data back to the server. Besides that, SSE does not support sending binary data, and you're limited in the number of SSE connections you can make from one browser. So while you absolutely could achieve a base level two-way communication using SSEs from the server and normal HTTP requests from the client, this process gets a lot more straightforward if you could just simply open one channel that either party can use to communicate with the other. And that channel is WebSocket. So since WebSocket is bidirectional, here's how the scenario would go down. Bob finds a GIF that he wants to send to Alice. He opens Worst app, which has just undergone a conveniently timed website update mere minutes before the scenario. Bob sends a WebSocket handshake request, which is met with a handshake response. This establishes a WebSocket connection between Bob's browser and WorstApp servers in which Bob is given a unique session ID. So Bob sends his gift to the server not as an HTTP post request, but as data with his session ID attached. The server receives this message, sees that it came from Bob, which is important since the server may have multiple connections open. Now here's where things get interesting. Since Alice also has WorstApp open, she has already established her own WebSocket connection between her browser and the server. Therefore, WorstApp sends Bob's message directly to her. Alice can then view this message and respond to it, sending information back to the server over that same connection. The server handles this, sending it back to Bob, and so on and so forth. So because this connection is open both ways, we've eliminated the need for long polling, as well as the needless separation between the methods of sending and receiving. And because of this, WebSocket allows us to write apps that have lower latency than other methods, making it a great choice for applications such as WorstApp. So that's an initial rundown of how WebSocket works to provide bidirectional low latency real-time communication using a fictional use case. Now let's look at some real-world examples of where this technology has been put to use. So what better way to find out where WebSocket fits into a company's tech stack than to hear it straight from the company itself? We'll go through a few examples. This first one comes from the blog of none other than Discord, well known and widely used, probably by some of you right this very minute. Discord is a social platform that uses WebRTC to handle its backend architecture for voice communication. But the usage of WebRTC doesn't mean that there's no room for WebSocket in their stack, right? So Discord's, I know this chart is scary, just bear with me. So Discord signaling servers maintain a WebSocket connection between the client and the Discord gateway. And this connection is used to receive events related to guilds, channels, messages, presence, etc. When a user joins a voice channel, they are assigned to a Discord server. The server is responsible for transmitting audio to the channel, and its status is represented by a voice state object. The client then opens a second WebSocket connection to the voice server, which is used for setting up media forwarding and speaking indication, aka the shiny green bubbles whenever you use your lovely voice. So next up, we have Slack. Without our organization's helpful Slack reminder about this tech talk, none of us would have remembered to attend it, including me. So Slack has a feature called Socket Mode, which allows developers to communicate with the Slack platform using WebSocket. This mode is particularly useful for devs who are working behind a corporate firewall or who have other security concerns that basically prevent them from exposing a public HTTP endpoint. Socket Mode allows your app to use Slack's events API and all the interactive components of the Slack platform without the public HTTP URL. Instead, using a WebSocket URL to communicate with your app. The WebSocket URL is not static, so it's created at runtime, which allows for greater security and the ability to develop behind that firewall. And unlike the direct HTTP endpoint, where the communication is unidirectional, WebSocket, as we know, uses a bidirectional stateful protocol with low latency to communicate between the two parties, in this case, Slack and your app. So in Socket mode, you're getting all the same functionality, all the same interactive components. It's the same API. The only difference is the communication protocol. And you can still switch between the direct HTTP endpoint and Socket mode anytime in your app's config. So Discord and Slack's documentation explain exactly how WebSocket can be used in a communication application, which I think is what comes to mind usually when you bring up WebSocket. But what about a completely different use case? So the last real world example comes from the documentation of everybody's favorite JavaScript module bundler, Webpack. Yeah, me neither. One of Webpack's great features is hot module replacement, or HMR, which allows developers to make code changes in their application and have those changes immediately reflected in the browser without requiring a full page refresh. So this feature is made possible by using Webpack Dev Server, which is a development server that listens for code changes and triggers a new build, keeping the generated bundle in memory. Webpack Dev Server uses the hot flag, which sets the server up in hot mode, automatically adding the hot module replacement plugin, which automatically adds the HMR runtime into the bundle. So this way, the server can communicate with the client to tell it when new code is available by opening a WebSocket connection. When a change is made to the source code, the Webpack Dev Server sends a message on the WebSocket channel to the client, indicating that there is new code. The client then downloads the new code and tells the HMR runtime to trigger two downloads. First, the new manifest of the new module, and then the actual code from the module that changed. The HMR runtime then loads the new code, calls the HMR API with the module hot accept function, which accepts that the module should be replaced. This way, only the new code gets re-rendered, making the development experience super smooth. So as we can see from our examples, WebSocket is a powerful technology. It has been widely adopted for real-time communication and web applications. However, like all things in tech, it's not the only solution for any given use case. And soon it may not even be a solution at all. Okay, so WebSocket was designed to meet a very specific lack of functionality in the hypertext transfer protocol. So as HTTP continues to evolve and update these problem areas, it's only natural that WebSocket would be impacted by these new developments. One such development is HTTP 2, which was introduced in 2015. HTTP 2 brings a number of new features to the table, including multiplexing and server push, which are capabilities that were previously only possible with WebSocket. And another development on the horizon is HTTP 3. Just keep coming, which is currently in the process of being standardized. So one of the key features of HTTP 3, which I'm very excited about, is the introduction of web transport, which is so new that it currently has an experimental technology warning on its MDN page. And, I think from here on out, when I start writing just questionable code that is frighteningly unpredictable, I'm just going to start calling it experimental technology, and then nobody can say anything. Why have pure functions when you can have pure chaos, right? So anyways, web transport is a new low-level transport protocol designed to provide low latency bidirectional communication, but with an emphasis on improved security and performance. In other words, web transport's purpose is literally just to be a better WebSocket. Now, while there have been developments that have brought some of WebSocket's features to HTTP, WebSocket is still widely used today and will continue to be used in the future. According to W3 Techs, less than half of all websites currently use HTTP 2. And so it's important to keep an eye on new technologies like HTTP 3 and web transport. But for the time being, it's clear that WebSocket will continue to play a vital role in real-time communication on the web. So let's review today's Tech Talk. First, we used a fictional messaging application to explore WebSocket's functionality as a bidirectional low-level real-time transfer protocol. Then we looked at documentation from real tech products explaining how and why WebSocket was used in their stack, covering use cases as common as communication and as surprising as hot module replacement. And then lastly, we explored some current and upcoming changes to HTTP that may influence the way WebSocket will be used from here on out. So in conclusion, things are looking good for WebSocket, but as always, the future is even more exciting. So I hope this talk was engaging, informative, and at least somewhat entertaining. God, we can only hope. Here are the great resources I use to further inform myself about WebSocket. And here is how you can reach me on LinkedIn and GitHub at DannyScript. Thanks again to Codesmith, Jeeny, and Bractlet for sponsoring this Tech Talk, and thank you all for attending.